In this lesson, we will look at the 4 different types of logic statements and one additional statement that is the result of 2 statements being correct. So the first kind of statement that we will look at is a conditional statement. Now, any logic statement has always 2 parts in it. One of them is the hypothesis and the other one is the conclusion. The conclusion is always followed by the hypothesis. So you always start with your hypothesis, and that hypothesis leads to the conclusion. Any logic statement is always started with the word if, and then you get the hypothesis, and then you have the word then, followed by the conclusion. So you start with the word if, and then you have the hypothesis, and then you connect that hypothesis with the word then, followed by the conclusion. So that's how you always set up a logic statement. Now, the conditional statement is one of those logic statements. There are 3 other types, and as I said before, one additional statement that results from 2 of these being correct. So let us get started by looking at the phrase, the statement, "On rainy days we will practice inside." We want to write this as a conditional statement. So we want to write it in such a way that it sounds like if, and then we write the hypothesis, then, and then we would write the conclusion. So in this case, what we need to do is we will look at this phrase and we will say, what part of this is the hypothesis? In other words, what is the part that is necessary to lead to the conclusion? And in this case, the hypothesis would be the rainy days. That rainy day will lead to the conclusion of practicing inside. So the hypothesis is rainy day, and the conclusion is practice inside. Once you've identified your hypothesis and your conclusion, you can make the conditional statement. Again, the conditional statement should read like this: if, hypothesis, then conclusion. Any logic statement should always have the words if and then in it. If you are missing those 2 words, it's not a logic statement. So if you now include the hypothesis after the word if and this conclusion after the word then, you get the following phrase, the following statement: if there will be a rainy day, then we will practice inside. Now you can change that to sound a little bit better grammatically, and so you could say something like, if it rains, then we will practice inside. So here is the if followed by the hypothesis, then followed by the conclusion. Again, a reminder here, if your statement would have read, if it rains, we will practice inside, you are missing the phrase, the term then, meaning you are not making a logic statement. So you need to make sure that you have both the if word and the then word included in your statement. Only then is it considered to be a logic statement. Let's say I have the statement, eating breakfast helps you focus more at school. So in this case, the hypothesis, the antecedent, is eating breakfast, because that leads to the conclusion, the consequent, which is focus more at school. To write this as a conditional statement, we would start with the word if, followed by the hypothesis. Then we would include the word then, followed by the conclusion. So it should read like this. If you eat breakfast, then you will focus more at school. If you eat breakfast, hypothesis, then conclusion, you will focus more at school. And so you keep going through the statements and identify the hypothesis and the conclusion, and then you set it up in between the words if and then. In the next example, your hypothesis is the right angle. That leads to a measurement of 90 degrees. Writing it as a conditional statement would sound like this. When you write that conditional statement, try to be as grammatically correct as you can. Make it into a normal sounding English sentence. In the third example, the statement is, on Saturdays, there is no school. So again, my hypothesis is the part that leads to the conclusion. Sometimes it's easier to identify the conclusion first before identifying the hypothesis. So what is my conclusion in this case? There is no school. And so that means that the other part of this statement is my hypothesis, which is Saturdays. And so now you can translate that into a conditional statement where you use the words if and then. So this is how you set up a conditional statement. A conditional statement always starts with the word if and continues with a hypothesis, and then afterwards has the then in it, continued with a conclusion. This is how a conditional statement looks like. Now, to make it more efficient, as we continue to look into the next kinds of statements, we will call the hypothesis, the initial hypothesis, we will call that P, and we will call the initial conclusion Q. In other words, if I want to take now this statement here, eating breakfast would be called P, focus more at school would be called Q, just to help us be more efficient. With that in mind, let's look at the second type of statement. The second type of statement is called the converse statement. So what you will do in this statement is you will flip the original hypothesis and the original conclusion with each other. So instead of going from P to Q, you will go from Q to P. Now, that means that Q becomes your new hypothesis and P becomes your new conclusion. Let us look at example 2 from the previous page. As a reminder, here is the conditional statement. If an angle is a right angle, then it measures 90 degrees. Now let's call the original hypothesis P, and let's call the original conclusion Q. What we want to do is we want to write the converse of the statement, which means we want to flip these around, but continue to keep the words if and then. And then you get the following. So we have flipped P and Q around, and we have made now Q the new hypothesis, and we've made P the new conclusion. If an angle measures 90 degrees, then it is a right angle. Now, hopefully you will see that this statement seems right, is good, and the conditional statement is good as well. So this statement is true, and so is this statement. Let's try the same thing with example number 3. The conditional statement had, if it is Saturday, then there is no school. Again, we will call Saturday the original hypothesis, we call that P, and the original conclusion, we call that Q. And for the converse, we will flip those two, keeping the words if and then in between. So we will get the following statement. If there is no school, then it is Saturday. So what we have done is we've taken our original conclusion and made that the new hypothesis. And we've taken our original hypothesis and made that the new conclusion in the converse statement. And some of you guys will probably have a weird feeling about this statement. See, you were fine with this statement, but this one gives you a weird feeling. And that's exactly what we want to get to. And that leads us to the biconditional statement. See, what we've done so far is we've looked at two statements, the converse statement and the conditional statement. Now, sometimes both the conditional statement and the converse statement are true, like in example 2. But sometimes they are not. So if both of those are true, like in example number 2, then we can call that a biconditional statement, and we can actually write it as a biconditional statement. However, if one of them is not true, then this is not a biconditional statement, which means it doesn't lead in both directions. And we will not be able then to write it as a biconditional statement. So the original statement, the original conditional statement, that the one that we had on the previous page, is called biconditional if it is true as well as the converse is true, always true. But if you can come up with a single counterexample against the converse, meaning proving that it is not always true, then your original is not a biconditional. So if P to Q is true and Q to P is also true always, then P to Q is biconditional, which means we can write it as P with both arrows pointing in both directions to Q. So P to Q as well as Q to P. And if that's the case, we write that statement in the following way. P if and only if, or short IFF, Q. And remember that P is your original hypothesis and Q is your original conclusion. So let us take a look at the second example again. We already said that the conditional is true, and just again to be more efficient, I will write down P to Q is true. Capital T stands for true. P to Q stands for the conditional statement that we had on the first page. And the converse is true as well. So P to Q is true and Q to P is true. And let me just point that out. If an angle is a right angle, then it measures 90 degrees. So every right angle measures 90 degrees, right? So that one is true. That's the conditional statement, and that one is true. P to Q is true. Then we wrote the converse. If an angle measures 90 degrees, then it is a right angle. That's true as well, because every angle that measures 90 degrees is called a right angle. So that's true as well. So that means the converse is also true. And if that is the case, then what we have is a biconditional statement. And if we have a biconditional statement, then we can write that statement as P if and only if Q. And so it would look like this. An angle is a right angle if and only if it measures 90 degrees. Now please remember that a right angle was our original hypothesis, that's our p-value, and measures 90 degrees was our original conclusion, that was the q value. So if you said an angle measures 90 degrees if and only if it is a right angle, that would not be the correct biconditional statement. Your biconditional statement has to start with the original hypothesis and lead to the original conclusion. In the spirit of being efficient, instead of writing if and only if, you can write IFF. And so it would look like this. Either one of those is fine. So let us go to the third example now. From the first page, this is our conditional statement, and that statement is true because if there is a Saturday, then there is no school. So we can say that P to Q is true. Now we have, up here we have the converse. If there is no school, then it is Saturday. Is that true? No, and the reason why that is not true, and this is our counter example. The reason why that is not true is because you could have no school also on a Sunday or on a snow day. So this is not always true. This statement is not always true. Q to P is not always true. The converse is not always true. And so therefore, this is not biconditional. Now you can't just leave this as the statement saying, oh, this is not biconditional. You have to support your argument by a counter or with a counter example. And I mentioned that counter example before already. On Sundays, there is no school either. That is one of your examples that you can give. Now we will look more at these counterexamples in the next lesson, but for now, you need to be able to say if something is biconditional or not, and if it's not biconditional, then you need to provide some kind of a counterexample. Now, as we determine if a statement is true or if it's not true, there are a couple of notes that need to be made. And the first one is that we always start from the point where we know or assume that the conditional statement is true. If the conditional statement is not true, then you've just simply been lied to and you won't get a biconditional statement at all because both of them have to be true. One example would be if a dog has 4 legs, then it is a cat. So that's definitely not true, so I don't even have to worry about the converse statement anymore. The other case would be a subjective conditional statement. That is the opinion of somebody or the decision that somebody makes. So something like, if it is Friday, then I go to the movies. Now that depends on the person that makes the statement, and in this case we will say that is considered to be true. So any subjective statement will always be considered to be true. So let's take this to the next example and we'll just summarize what we have at this point. So we know how to write a conditional statement, how to write a converse statement, and then determine if it is biconditional. And then if it is biconditional, we can say this is how you write it as a biconditional statement. And if it is not biconditional, then we can provide a counter example. So the first goal is, in this case, to write the converse of this conditional statement. Flipping the original hypothesis with the original conclusion, flipping those two around, you get if x is equal to 5, then x plus 2 is equal to 7. So now you have to determine in the second part of the question, is this statement biconditional, which means is P to Q correct and is Q to P always correct? So we can say that 5 plus 2 is equal to 7. So x being 5 is the right conclusion for this hypothesis. So P to Q is true. Now we will look at Q to P. If I know that x is 5, can I always conclude that x plus 2 will give me then 7? In other words, 5 plus 2 will give me then 7. I can do that, yes. So Q to P is true as well. If both the conditional and the converse are true, then what we have is a biconditional statement. And if we have a biconditional statement, we can write this statement as a biconditional statement, and it would look like this. X plus 2 is equal to 7 if and only if x is equal to 5. Let's look at the second example then. Again, my first goal is to find out what the converse is. And now my second goal would be to determine if the conditional statement is true and if the converse statement is true. If it is a dog, then it has 4 legs. Yes, the conditional statement is true. What about the converse statement? Q to P is, if you look at this, you should see that Q to P is not true. Why not? Because if it has 4 legs, it doesn't mean that it is a dog. It could be something else. So Q to P, the converse statement, is false, which means that we do not have a biconditional statement. This is only part of your answer. Your other part of the answer needs to provide a counterexample. And so here would be one of those choices that you would have. If it has 4 legs, then it could be a cat. And so that's how you deal with a biconditional statement. A conditional statement can be biconditional if both the conditional and the converse are true. And if that's the case, you need to represent it as a biconditional statement. However, if your conditional is true but your converse is not true, then you don't have a biconditional statement. But you need to provide a counterexample to prove that your converse statement is not true. So that is the setup of logical statements. We've covered 2 of those, plus that special case where both the conditional and the converse are correct, are true. Now the next two biconditional statements are on the bottom of this page. And since we have looked at the notation and we know how to use the notation now, we can go from the first conditional statement and we can write the next kinds of statements again. So at this point, all you need to be able to do is take your conditional statement, identify the P and the Q of your conditional statement, and then be able to use those to make an inverse statement. Now, an inverse statement has this symbol in it, P, leading to this symbol, Q. As a reminder, this symbol means not. So you are negating your conditional statement, making it negative, we say. So if the conditional statement is, if it is Monday, then it is a school day, the inverse statement would be, if it is not Monday, then it is not a school day. And here's another example of that. So you're keeping the P value in the beginning, the Q value. You're keeping the P value as the hypothesis and the Q value as the conclusion, but you are negating both of those, making both opposite. Now, instead of using this as an example, let me choose something different. Let's say if a number is odd, then it is not divisible by 2. Now, the inverse statement for this statement would keep the P value as the hypothesis and the Q value as the conclusion, but it would make this and this one, it would make them opposite. So it would look like this. If a number is not odd, then it is, since I had the initial one being not divisible by 2, what is the opposite of not divisible by 2? The opposite would be divisible by 2. If a number is not odd, then it is divisible by 2. So that would be the inverse statement of my original conditional statement. And then we have the contrapositive statement, and the contrapositive statement reverses the hypothesis and the conclusion from the conditional statement, and it makes them both negative. It negates both of them. So if the conditional statement is, if it is Monday, then it is a school day, the converse would flip those two around, and it would say, if it is a school day, then it is Monday. And the contrapositive statement takes it one step further and negates both of these, makes them both the opposite. If it is not a school day, then it is not Monday. And the inverse statement would do the same thing, but to the conditional statement. So if it is not Monday, then it is not a school day. So here's one more example. The conditional statement is, a number is even. If a number is even, then it is divisible by 2. The contrapositive would flip these and make them both negative, or give you the opposite. So that would mean, if it is not divisible by 2, then it is not even. If it is not divisible by 2, then it is not even. So that would be the contrapositive statement. So your goal in this lesson is simply to be able to make conditional statements, make converse statements, inverse statements, and contrapositive statements, in addition to determining if a conditional statement is biconditional.